Okay, this is a simple problem on relativistic time dilation for Physics 1000 at Auburn University. So a typical problem might look like this. You're given that a rocket is traveling at a speed of 0.8 c relative to a stationary observer. So the stationary observer is what the figure you see down on the bottom. This is the stationary observer, and this is the rocket who's traveling at this velocity relative to the observer. So the observer's standing still, the rocket's going at 0.8 c, or 80% of the speed of light. And a typical question might ask you, for some time interval that you experience here, you being the stationary observer, for some time interval t, what is the corresponding time interval experienced by an astronaut aboard the rocket ship, which will be t naught. I should mention t naught is also called the proper time. It's the time experienced in the moving frame of reference. So, just to recap, because the terminology can get kind of confusing, you are the stationary observer, and the question is formulated such that for some time interval for you, what is the corresponding time interval for the rocket ship? Let's put some numbers with it and do an example. You get rid of these lines. Let's say that the question asks you measure on your watch an interval of 10 seconds. And we want to know, in that 10 seconds that you experience, how much time passes for the occupant of this rocket ship, this t naught. This is what we're solving for. And we have at our disposal this equation. T is equal to gamma t naught, where gamma, if you recall, let me go to a different page. Gamma is this quantity here, 1 over 1 minus v squared over c squared, and that whole quantity is under the radical. This is our dilation factor. We're also going to see this again when we get to length contraction. But let me rewrite the formula. What we have here is T is equal to gamma T naught. Now let's ask ourselves, what do we have and what do we want? Well, what we're given is that this T, this is an hour frame of reference, we're the stationary observer, is 10 seconds. And we're given gamma. If you notice, I'll just put a star there, just say that this is given. If you notice, gamma involves the velocity here, which we know. Everything else in there is a constant, so we know what gamma is. Our unknown here is t naught. So we do what we've done all semester. We solve this equation for t naught, the time experienced by the astronaut. So if we do that, what we come up with is t naught is equal to t, our time, over gamma. And from there, we can do something, we can plug in some numbers. I'm going to do this in steps to show you the trick with gamma. So let me once again go to a new page briefly and show you the easy way to calculate gamma. I'll rewrite what it is here. 1 over 1 minus v squared over c squared. The whole quantity is under a radical. So we're given, notice, v in terms of c. We're given that v is 0.8 c. And if that's the case, this actually becomes pretty easy. Because then, notice that v squared is equal to 0.8 squared times c squared. C is just a number. If I square this quantity 0.8 c, what that turns out to be is 0.8 squared times c squared. Now if I plug that back into my original expression for gamma, and I'm going to have to write a little large here, I get 1 over 1 minus, I'm going to write it down exactly what I wrote up here, 0.8 squared, should put that in parentheses, times c squared, and that is over c squared. Well, look what happens. There's some magic going on here. Just to be explicit, I should put a radical there. And so the magic here becomes that c squared over c squared is just 1, right? So this whole quantity becomes 1 over 1 minus 0.8 squared, and that is under the radical. Now if you plug that into your calculator, what you get is that the value of gamma for our case Remember, point 0.8, there's nothing magical about point 0.8. That was the number we were given. If you plug that into your calculator, you get that gamma is somewhere around 1.67. The 6 is repeating. But that's our value of gamma. So now let's go back and plug that into our original equation. What we had here, T naught is equal to T over gamma. That equals to 10 seconds over 1.67. And what that comes out to be is about 6 seconds. So what this says, now let's pause and let's pause for a second before we talk about what it means and recap the math. So what I'm given, let's go back to that page. I'm given that there's a rocket traveling at 0.8 c, which is 80% the speed of light. I'm given that, as for me, a stationary observer on the ground, I notice 10 seconds pass on my watch, and I'm curious as to how much time passes on the astronaut's watch in that, from my perspective, in that same amount of time. In other words, if I get a telescope and I zoom in on this astronaut's watch, as I'm watching 10 seconds pass off my watch, what do I see click off his? We know that time is going to run differently in these two frames of reference because of the relativistic velocities, but I'm curious, as if I'm looking through my telescope, how do I see his watch move? How much time passes off his watch while 10 seconds passes off mine? So I use the equation I have here, T equals gamma T naught, with T naught being his time, T being my time. And then I solve that expression for my unknown. In this case it's T naught. And that's what I've done here. Let me change colors. That's what I've done here. I solved my expression for my unknown. And then I took a slight detour, which you don't have to. You can do all this in one step. But I took a slight detour here and calculated gamma. And I did that to show you this trick here. This nifty little trick where the c squareds cancel. As long as your velocity is expressed in terms of c, that will always happen. And you just get a pure number for gamma. And then after I did that, I went back to my equation where I had solved for my unknown. I plugged in my numbers, and what I got was 6 seconds. So that's the math. Let's talk about physically what that means, which I've touched on already, but just to recap, because this can be kind of confusing. That means, let me go back here, as I'm watching this rocket ship go by, and as I get my telescope, and I zoom in on this astronaut's watch, if I click off 10 seconds on my watch, what I see click off of his watch is 6 seconds. Now, of course, in his frame of reference, he doesn't notice any bit of difference as far as how he's living, how the universe is progressing. He experiences time normally. But how I see it is that he only ages 6 seconds while I age 10 seconds. You can imagine if this were to go on for some time, I would continue to get older at a faster rate than he does, which is what we touched on in class a little bit with the twins paradox. So that is a simple problem for relativistic time dilation. It's not going to get a whole lot more complicated than that in this course. So that's the video for this. There will be another one on length contraction.